Hello, now I will talk about the second task. It is a logistic regression and gradient descent exercise for the iris dataset. So in the beginning, we load the dataset as it was shown in our videos lesson, and the next step is we divide it by the training. We divide the dataset into training and testing data sets subsets by 20 and by 80 and 20% respectively. Then here we define a logistic regression function for binary classification. It takes the x features or data, and it takes also the labels. So, and here it represents number of features. Well, actually it represents number of d plus 1 features. So there are 4 plus 1 and 5. So, and we create such size of weight vector empty, then we initialize its first values randomly here. Then the t, it is the number of iterations, 2000, and the eta represents the step size of 0.001. Here wt, it is a matrix, empty matrix at this step, at this moment, to store all 2000 weight vectors, which we obtain when we iterate 2000 times. So in the beginning of the in our first iteration, well, actually in this for loop here, each time we randomly pick data set, we randomly pick a sample from our training dataset from 0 to 119. It is like 120 data sets for training. And for then the chosen sample is stored in this xn and the yn. Yn is a label. So we augment the data set by 1. We add it, so we can do inner products later when we calculate the gradient here. It is the formula of gradient which was found in the lessons, and this part, this bracket, it is a sigmoid function. So then, to update our weights, we multiply it by step size, and we add it to our current weight vector. Then the new weight vectors, we store all of them. Like when we iterate 2000 times, there will be 2000 updated weight vectors. Then we all store them into this WT matrix. So and we return it. This is our function. We will use it in this section where we are performing one versus all classification. So in the iris dataset, there are 3 classes, 3 types of flowers. They are classified as 0, 1, and 2. So there are in general 3 classes. So we create a matrix here with 3 by it's actually 3 matrices of the size, each of the size 2000 by 5. And here we just do the same. We create a training matrix for the labels of the training dataset, which will store 3 different labeling styles for the first class and the second class and the third class. So there are 3 by 120 matrix. Then the test y, okay, it represents the similar matrix but with the size 3 by 30. So each time in this loop, k represents the value of the class in the iris dataset. So the first iteration is equal to 0. So we make the labels -1 or 1, where 1 represents the first class, and in the second round, in the second iteration, k equals to 1, and this time 1 represents the second class. And in the third last round, k this part where 1 will represent the third class. So we store all 3 ways of labelings into this variable. Then we feed it into our logistic regression function here, and we obtain all the matrices of weight vectors. So what we do next is that we calculate the in-sample error. We iterate through all iterations, 2000 iterations, and for for the weight vector in one of them, in one of the iterations, we check it for all our dataset here, training dataset, 120 samples. What we do here is that we calculate this product between inner product of weight and our training data. Well, x0, x1, x2, they are the same. Just for the convenience, I wrote it like that. Well, they are the same training data because they don't change, only labels change. So after calculating G0, G1, and the G2, G2, what we do is that we create an array in such manner where G0 stands in the first position and so on. We are interested in finding in the arc max, which means like the indices. So the index of the maximum value here will represent the label actually, because they correspond. The first index, like 0 of the zeros class, this index 1 of the first of the class 1, and such and so on. So the outputs of G can be either 0 or 1 or 2, depending on the maximum score. Then we see if the output of the G is equal to the training data. If it is not equal, we increment the training error. Let me stop here.